Welcome to the next session of fluid mechanics. In this session, we are going to discuss about classification of fluids. In the previous lecture, we have discussed about Newton's law of viscosity. We saw that tau, that is shear stress, was directly proportional to the rate of shear strain or velocity gradient, as you can call this term. When I substitute this proportionality sign with an equal to sign, I had used a constant of proportionality which was mu. Tau is equal to mu du by dy. We said that any fluid which follows this law, that is, as stress increases, the velocity gradient increases, and as stress decreases, velocity gradient decreases. That is the meaning of tau being directly proportional to du by dy. So any fluid which follows Newton's law will be called as Newtonian fluid, and any fluid which does not follow this law will be called as non-Newtonian fluid. So in this class we are going to discuss about the classification of fluids based on this criteria. So first we'll talk about the Newtonian fluid itself. So here I have jotted down all the fluids that we are going to discuss. The first one being the Newtonian fluid, wherein n is equal to 1. Now I wrote tau is equal to mu du by dy. It is always raised to n. When this n is equal to 1, it is linear. We say it is Newtonian fluid. Air, water, kerosene. These are some examples of Newtonian fluid. So I can draw Newtonian fluid, that is tau is directly proportional to du by dy. So it will be a straight line because n was 1 which was passing through the origin, and this is how I am going to draw the line. So this is the graph for a Newtonian fluid. The next type of fluid is called as pseudoplastic or shear thinning fluid, where the value of n is less than 1. The equation remains the same. Tau is mu du by dy raised to n, but n value will be less than 1. So I can have, say, n value is 0.2, 0.3, 0.4, etc. Any value which is less than 1, up to 1 but less than 1. So they are all included in pseudoplastic fluid where n is less than 1. Some of the examples being blood, paint, alcohol, toluene. These are some examples of pseudoplastic fluid. Now it is called as shear thinning fluid because when you apply the force on these fluid layers, what happens is your fluid becomes thinner. When I am talking about viscosity, it actually becomes a little thin. Hence it is called as shear thinning. When you apply shear, the fluid becomes thin in nature. Now since n is less than 1, mathematically this graph should be above this line. So it is over here. This is n less than 1. This is pseudoplastic fluid. Next we will go for the third type of fluid, which is called as dilatant or shear thickening fluid. Now by the name you must have understood shear thickening, which means when you apply force on these layers to pull them apart from each other, or say if you remember the example wherein one plate was fixed and the top layer of the fluid is being pulled with a particular velocity. So when you are applying a force of this sort, there will be shear induced. So the shear causes thickening of the fluid. That is called as shear thickening fluid or dilatant fluid. Some examples are cornstarch, honey. You can see here n will be greater than 1. The equation is same. Tau is mu du by dy. N greater than 1, which means n can be, say, 1.1, 1.2, etc. So these are the values which can be for a particular type of fluid of dilatant type. N is greater than 1. So my graph will be below this line from here. This line. N greater than 1. Now fourth type is called as Bingham fluid. For Bingham fluid, n is equal to 1. The examples for this type of fluid is toothpaste, mayonnaise, chocolate, mustard, and many more. Now we need to focus on this equation. If you look at the equation, it is tau is equal to tau y plus mu du by dy raised to n. When I had tau is mu du by dy raised to n, my lines were passing through the origin. But now if you observe, it is tau is equal to tau y plus this term. So this tau y is nothing but a value. So on this axis tau, you will have some height. This will be called as tau y. Tau y stands for yield shear stress, which means suppose if this is your surface and you have some fluid layers here, you are applying some velocity u, but for some time you will not observe any movement in the layers. It will take some time to yield, that is to start to flow. So that is called as yield shear stress. Now as you heard very correctly, there is some time requirement. Hence you will observe here, I have written that this is a time dependent viscosity, which means after some time the fluid starts moving. So there is a time required for the movement. And when I say the fluid starts moving, obviously viscosity term comes into picture. When I talk about Newtonian fluid, shear thinning fluid and shear thickening fluid, that is pseudoplastic and dilatant, these three are called as time independent viscosity, because you can observe as you apply the force, immediately you will see some kind of motion in the fluid. So they are time independent viscosity, immediately movement takes place. So when I plot Bingham fluid, if you observe carefully, n is equal to 1 and tau plus some term. So this is the tau y, and then I will drop Bingham fluid in this fashion. This Bingham fluid is also called as an ideal plastic fluid. Next I have thixotropic or shear thinning fluid. Here n value is less than 1. Again shear thinning meaning you must have understood. Thixotropic has this equation, tau is tau y plus mu du by dy raised to n. Here n was equal to 1. Here n is less than 1. So again we can have these values here for n. Example of thixotropic fluid are gelatin, printing ink, milk, colloidal suspensions, etc. So let's plot thixotropic fluid. Since I said n is less than 1, so like pseudoplastic, this will be above the Bingham fluid. And last we have Rheopectic or shear thickening fluid. N is greater than 1. This is the equation. So n greater than 1 means I'll have these values of n over here again. Some examples of Rheopectic fluid are gypsum paste, synovial fluids, cream, etc. Synovial fluid is a fluid in the joints. So these are some examples. So let's plot Rheopectic fluid. It will be drawn here below, because n is greater than 1. So these are the classification of fluids based on their nature. I hope you have understood the lecture. If you have any doubts, please write to me in the comment section. See you in the next session. Thank you.